invite me. It was a very nice conference. I'm going to talk about fermions coupled to Hopf Solitons, and I'm going to spend quite a bit of about skyrmions coupled to fermions. So I'm going to start with the motivation. Then I discuss what we know about skyrmions and what we know about Hopf Solitons, and why the sphere is particularly interesting in this case. I say a tiny bit about fermions on the sphere, and then I talk about the results we have. I have to admit, most of the results are going to be for skyrmions, but so I can see some hints of what to do with Hopf Solitons. So, I mean, one of the motivations is the similarity between skyrmions and Hopf Solitons. And for skyrmions, we have this sort of idea. There was sort of a long discussion. The Skyrm model came up, and then we wanted to quantize the Skyrm model as a fermion, and there were sort of different approaches. And one approach was what Martin did with the Finkelstein-Rubinstein constraint, and the other approach came more from the sort of back models and things, that you were coupling the pion fields to fermions, and you were seeing how the resulting spectrum looked like, and there was sort of an idea of trying to understand the fermionicity, so the fact that skyrmion is fermionic by solving some Dirac equations in the background of a skyrmion, and then you see some zero modes, and when you find your zero mode, then you can argue that this is possible. So what I found is that if you go to the sphere, you can do these kind of things. So exactly, there's some exact solution. So this is sort of my main motivation, but there's also quite a lot of recent interest in this. So there was a paper on topological superconductors, so topological insulators, and they had they basically had the same Lagrangian I'm going to look at, the same kind of coupling in flat space. And they were also interested in the question where you can think of this excitation as a fermion. And their answer was yes, and they did some numerical calculations. There's also some alternative QCD proposals where you use adjoint quarks, and then you also get these Hopf Solitons and a similar coupling term. Antiniemi did something on fermion number in knotted soliton background, but this is a slightly different coupling term, but it's sort of related. Okay, so skyrmions. There's lots of different ways of writing down the Skyrm energy functional. This is sort of more the one which you would use for in numerical calculations. So you have you have a map from space which is 3 plus 1 dimensional, so 3 spatial dimension and 1 time dimension, and you have a field which is in the group SU2 if you want, or you can also think of it as living on the sphere. So it's living as 4 components together with the normalization condition that's equal to 1, and the vacuum is just the value at infinity is just the point 1, 0, 0, 0. So in some sense, the old interpretation in terms of sigma and pi fields, the pions are all 0, and the sigma field is 1. So this kind of thing has a topological charge, which is the Winding number. We've seen this before. Solutions are localized, particle-like. There's the steric theorem, which Martin was mentioning before. We have a topological bound, and they come from Bogomolly equations. So the Bogomolly equations is basically you kind of complete the square. So you can rewrite the energy functional as some kind of square and the topological term. And if you can, so the equations in the square, they tend to be of first order, and if you can solve them, then you know that you have achieved the bound. Unfortunately for skyrmions on flat space, this is not possible apart from the vacuum, which is pretty boring. But on the sphere, if you have a sphere of radius 1, then the solution is just the identity map, but it satisfies the Bogomolly equation. Furthermore, the identity map is a global minimum in the charge 1 sector in the sphere, provided the radius of the sphere is not too big. Because if the radius gets bigger than square root of 2 in the units I'm using, then there is a phase transition where basically the skyrmion wants to be more on one of the poles. It wants to localize that around sort of one of the poles rather than being delocalized across the whole sphere. Okay, so what's the story about Hopf Solitons? Well, if you write down the Lagrangian, it's basically the same. Apart from that, now you have a 3-component field, and the normalization condition is, well, usually, again, you have at infinity you're mapping to a point. Topological charge we have seen before and described by various other people, but this is pi 3 of S2, so I'm not going to say anymore. Again, there's the steric theorem, so the localized, but now they're string-like, that is not like solutions, string-like solutions, and we have this energy bound, which has this funny power. But again, we have sort of two special solutions. One is the vacuum solution as top chart 0, and then there's another one which is the Hopf map, which Martin used in his previous talk. And again, there was a calculation by Ward that the Hopf map is a global minimum in the charge 1 sector, provided that the radius of the 3-sphere is less than square root of 2. So that's sort of an analogy. I mean, this is basically where the Hopf map does work for Hobson. Good. So what about fermions? Well, when you put, we want to couple fermions to skirmions and to Hopf Solitons to just sort of get an idea of how they behave. So first you have to sort of understand how fermions in general live on the 3-sphere. And basically what you have to do is calculate a spin connection. So this is fairly standard. So you write this down, you have these frame fields. So in one way of doing this is using stereographic coordinates. The metric looks like this. And then if you calculate, you get a spin connection, which is basically this x here. So there's some calculations. But this is sort of the kind of, there's sort of one additional thing you have to take. Well, first the derivative changes because of the frame fields, but then the spin connection comes in. So we want to couple. So for skirmions, there's a standard chirally coupling term where so gamma 5 gives this chirality, and so you couple your skirmion sort of in the middle between psi and psi bar, which gives some kind of, you can think of this as some kind of space-dependent complex mass term, or so. Anyway, so you get something like a mass term. So on the 3-sphere, I can write a skirm field. Basically, just so I think of one of my angles on the 3-sphere. I have 3 angles, so I have 2 angles which are the normal 2-sphere, and then there's another angle which sort of tells me where the 2-sphere is, and this is sort of the analogy of the kind of radius. If I would project back to flat space, then this angle would correspond to the radius. So you can write this like this. So I get cos f times sin f times this unit vector which points in the normal 2-sphere, which is sort of the normal 2-sphere of directions. And then if I set this f of chi equals b times chi, this gives us the exact solution for the vacuum for b equals 0, and gives us the exact solution for b equals 1, and it also gives us some approximation for b equals 2 and 3, which we will see later. The interaction term, which I found in the literature for the Hopf Solitons, is very similar. Basically, you just leave out the first component. Right, and then the vacuum, unfortunately, is no longer 0, 0, 0, but 0, 0, 1, which causes a bit of trouble. So we can do the same thing. Anyway, so this is the coupling term. So now the next few slides I'm going to see what happens for skirmions. Okay. So if first of all I write my equation in terms of polar coordinates, I use the e to the IET to go to sort of a time independent Schrödinger equation to calculate the energy eigenvalues, which I'm interested in. And then, well, I have to set up a little bit. So my psi is a Dirac spinner, so it has 4 components, but there's also the skirm field. The way the skirm field act on it is by sort of isospinning. So I have a there's actually a spin isospinner. So you can think of this as a 2x2 matrix. So these two components as 2x2 matrices, and on the one side I have the sort of the arc spinner X on it, and on the other side I have the sort of SU2 degrees of freedom, which comes from the skirmion. So this sort of internal degree of freedom acting on it, and both of them are sort of Pauli matrices.
Composite connection and couple it to fermions in the usual way as for
I can couple in different ways. So I'm coupling this way. Yeah. I mean it's a standard Lagrangian, but it's not the only Lagrangian to do it. Okay, so if I do this, I get some kind of momentum operator. So this is my P, which has the angular momentum in it, and so on. And so what makes this all possible is that I can define this grand spin. So I have this big spin operator which has the orbital angular momentum, the spin and the isospin operator in it, and this commutes with my Schrödinger equation. Okay, and because I can do this, I can use. I mean, details are not so important, but I can write down the eigenfunctions. There's sort of 4 different ways of writing down states with grand spin G and so third component M. And if I insert it into the Schrödinger equation before, I get these sort of coupled differential equations, and I get another set if I. So this is sort of one parity state, and if I sort of switch this round, I get the opposite parity. And on the level of equation, all this does is it changes G to minus G. So this is kind of. So I have this sort of big set of equations, but if I change G to minus G, I just change sort of the parity of the solutions. This is quite useful because when I draw my spectrum, I can draw from minus G to G, and then I say, well, one of them is the negative parity state, one is the kind of positive state. Okay. So for the vacuum, basically what I end up is I get massive fermions in the 3 sphere. And I can calculate the energy, and I can calculate the. So in this case, these 4 equations decouple into pair of 2 differential equations, and what you get is these Jacobi polynomials, and then you can calculate this sort of in detail, and the results agree with Camporesi and Higuchi, who did the same thing in n dimensions, but for massless fermions. So what happens when I go to this non-trivial case? So then I have still 4 equations, but the surprising thing is that I can solve them. So I can solve this explicitly, and together with my PhD student, we wrote down all the different eigenfunctions. So I mean, I think it's always good if you calculate something completely analytically, because this gives you a way of testing your ideas and verifying things which other people did numerically and sort of other situations. So what is the spectrum? So there's the red line is kind of the most interesting one. The red line is one which starts at the positive spectrum and then goes over to the negative spectrum, and at some stage in the middle, sort of for G equals 3/2, you get a zero mode which you can interpret as a fermion sort of bound state of a fermion and this background skirmion. Yep. And well, if you look at the other parts of the spectrum, so there's the blue lines, they're sort of shifted a little bit, so that they are sort of, for one parity you get one side, for the other parity you get the other side, whereas the yellow lines, which are not very easy to see, they are symmetric. So in particular, there's sort of a correspondence between the topological charge and how many zero modes do we get. So how many modes come from one side and go to the other side. So when I go to these other configurations, so this is charge b equals 2 and b equals 3, then you see that there's again I have this crossing, and now crosses sort of twice, once on the one side, once on the other side. And if I look at the other picture, this is for b equals 3, I have 3 crossings, 1 on one side and 2 on the other side. So basically there's this sort of understanding that if you have b modes cross 0, where b is the topological charge of the Skirm field. Okay, so then the question is, can I reproduce some of this for the Hopf Soliton? Well, so there are kind of 2 questions. I've managed to calculate the spectrum completely analytically and explicitly. Can I do the same thing for Hopf Solitons? And does the spectrum has a similar dependence on topology? So so the interaction for the Hopf Solitons is basically this part with the where I have my tau dot phi basically as this coupling, and my phi is basically 0, 0, 1 for the vacuum, and it's the Hopf map for for charge q charge 1. And the sort of the big problem is that the angular momentum doesn't commute with this interaction term anymore. Can I save anything? Well, when I do the interaction term for the vacuum, then so G3 should have an operator on it. So the third component of the angular momentum commutes with the still commutes with the interaction Lagrangian, which means that I can fix my third component of the angular momentum, and this gives me a way of sort of playing around with it. But the interaction term then basically it mixes up G, but it doesn't mix them up very badly. It just mixes G with G plus 1, and it turns out that it's sort of similar. You can make a similar ansatz and still give rise to 4 coupled ODEs. For the Hopf map, it gets a lot harder, because now the Hopf map, if you write this in polar coordinates, there's all kind of terms, and it's still true that G3 commutes, so M is conserved, but it couples to lots of different G states. But on the other hand, this is something we want to. I mean, for the Skirmion, if you look at the 0 mode, it's basically just the mode which is localized, which is kind of delocalized on the Skirmion. It's sort of a very boring mode. Whereas for the Hopf Soliton, what you expect is, well, you have this sort of twisting, so you expect that something more complicated comes out of it. So I mean, in some sense, you expect that it's going to be more complicated. And well, this is my conclusion. So I've discussed how to couple Skirmions and Hopf Solitons to Fermions on the 3 sphere, and we showed this spectra, and they did kind of had this nice flow. Hopf Solitons are just more complicated. Some things generalize, but others don't. And it's possible to calculate the spectra in the vacuum state, and there's some hope that you can write this down explicitly. But the low state for the Hopf map is more complicated. Good. So I stop here.
Thank you very much. Questions?
So this observation that the number of 0 modes is related to the topological charge, is that something you can prove, or just you observe it?
There's no proof, I understand, but
well, can other people prove it? Or
there's some attempts, but basically you have to. Well, you go via instantons, and then you say something that you construct an instanton, which kind of translates the Skirmion to the vacuum, and then you say something about what the Fermions do with the instantons, and then so this is a way of understanding it.
Yeah.
Nick?
There was some work by some Japanese on Skirmions, I guess in flat space, coupled to Fermions.
Mm-hmm.
They did a lot of numerical work. They partly answered your question again numerically.
Mm-hmm.
It seemed to be an accident, this relation between sort of low-lying modes or 0 modes and the baryon number. I wondered if your results overlap theirs.
So an accident, but it still always works. Is this sort of the feeling?
You alluded to this beginning of your talk,
Yeah.
sort of bag models,
Yeah.
coupled to fermions.
Yeah. So
You actually compare in detail anything?
not with this particular group. No, not no.
Because your skirmion is always on a 3 sphere.
Well, I mean, I like it because I can actually do something, and I need this huge amount of symmetry to to do it. I mean, there's one thing I didn't mention is for b equals 1, I can take some sort of arctan ansatz for the shape function which localizes, and I can follow the zero mode numerically. But then, as the more so complicated I make my model, the less I can do. Exactly. So then my methods are no longer appropriate, I think.
It's clearly a future direction. Thank you very much.